All right. Okay. Well, good morning and happy Monday. I hope you guys are doing well. We'll go ahead and begin. Thanks for voting and yeah, so this week we will do classes online and then next week we will return to in person. Um, okay. So let's pick up where we left off, where we were talking about maximum likelihood estimation of our parameters, and then we did um, and we found for kind of linear regression that minimizing the sum of squared residuals and maximizing the likelihood of your data if you assume your data, the errors in your data are normally distributed, we found that those things produce equivalent results. Here, we want to look at the variability in the predictions themselves, okay? So we have right here, as far as the values, our predicted values go, we have, our estimated weight parameters multiplied by any kind of new observation X, the new values. And basically, you just kind of take the product of those things, right? So, in a linear regression model, if you say, hey, make a prediction for this observation where X1 is 3 and X2 is 4, basically you just plug those numbers into your linear regression equation, which will be, take the intercept plus, your weight, your beta 1 or your W1 coefficient times X1 plus your W2 coefficient times X2, and then you add them together. And that's equivalent to just doing kind of your estimated parameters multiplied by your new observation. We might also want to know what is the variance, okay, of this kind of new the new value that we get, right? What's the variance there? And so that is going to be sigma squared times kind of X transpose X inverse X new, okay? So this is a little bit strange, but you take the entire X matrix and you go X transpose X and you invert that. And then you kind of basically multiply by your new observation, you multiply it by kind of the population variance, and this will kind of factor in, what is the variance or variation for your new predictions. So the idea there is, okay, let's say we have a new observation. X1 is 3 and X2 is 4, okay? I create a model based on some data, and so I get a certain slope and I get a certain intercept, intercept and W1 and W2 parameters. I estimate those based on my data. And so I say, based on my data and this new observation, I predict the value is going to be 27. I'm just making that up. Okay. If somebody else were to try to create the same model, okay, and say, all right, I want to make a prediction. They gather some data. Their data is slightly different from mine. They fit a linear regression model. So they end up getting a slightly different slope and intercept. And they plug in this new observation. X1 is 3 and X2 is 4, or whatever I said. And they say, okay, well, according to my model, my prediction for this observation is going to be, I don't know, 22. Okay. Somebody else fits another model. It's the same model, but different random sample of data. And when they use their random sample of data, they get different things. And basically, how much variability will there be from one prediction to another prediction? That's kind of what we want to know. Okay. The variability in the different predictions. So let's let me just kind of illustrate what this ends up looking like. Okay. So when you look at the variance of the predictions, the sigma squared, it takes the variance of the population, and then you kind of takes into account the value, your new value for x, along with kind of all of the x values that you've seen so far. So, so if the values we've seen so far are for x is 1, x is 2, x is 99, x is 100. So this is, I'm just fitting a very simple linear regression line. I just have a slope and an intercept. So the intercept terms align with the ones, and then the slope terms align with these values, 1, 2, 99, and 100. Okay. So this is going to be my x, and so you'll see I have x transpose x, okay? And then my new observation is going to be, we'll have an x value of 50, right? And so, so basically, what is the variance of my predictions going to be? It's going to be something like this. If I'm going to do x new, x transpose x inverse x new. So I'm taking my x new, my new observation, doing x transpose x inverse, and then taking my new observation over here. And we're going to assume sigma squared is just 1. And then, so in that case, so how much variance is my prediction going to just exhibit? Only a little bit, 0.25. Only 0.25, okay? And so the idea here is you've got, you have an observation at 1 or 2, an observation at 99 and 100. And based on that, we're going to try to make a prediction, okay? And here, x new is kind of like right in between these two. And so there's not going to be a ton of variation, all right? So it actually doesn't matter. You'll notice, as far as the variance goes, only the x values are in there. The actual y values don't matter. You just need to have an overall measure of the variance in y, okay? And so if we assume kind of just this constant variance in y, this is kind of what the picture might look like, right? So again, I observe some values. I get a random sample, and I fit a fitted line. I make a linear regression model. Maybe I get this blue line right here, okay? So I pick some random values. My random values for x are 1, 2, 99, 100, but I get, I'm sorry, not my values of x aren't random. They are 1, 2, 99, 100, but the actual associated dots are random. They exhibit some variation. So based on the ones I get, maybe I fit this blue line. You take a sample of data. You get a measurement of x at 1, 2, 99, 100. Okay. And you fit and so maybe you get different dots, okay? And because there's random noise, maybe you get, I don't know, this dot up here and that dot over there. And so you fit your line and you get something else. Maybe it's the green line, okay? Somebody else fits another line, okay? And they get something else. And you can see that if you're trying to make a prediction near when x new is around 50, the amount of variance that we exhibit is a lot is quite small. It's only around 0.25, right? I guess I just want to kind of check in and make sure this logic is reasonable and makes sense to you, or even this concept of like variation in predictions. How do we do this? It's hard to see. I don't know. I don't know if you guys are willing to have your cameras on. It's like bad memories of learning from a few years ago. But um, you can have your cameras on. That's always appreciated. Or you can give me some thumbs up feedback there. Okay, so this is what it looks like. All right, thanks for that thumbs up. Okay, all right, let's just kind of take a look here. This time, my X values that I've observed are at X is 1, 2, 3, 4. Okay. And then we're going to put in a new observation at X is 100. Okay. So, I mean, we already know this is a bad idea. This would be like extrapolating and stuff. But look at the variation. It is huge. Okay. It's like 1,900. 1,900. All right. You go back here, the variation was 0.25. And over here, the variation is huge, 1,900. Okay. And so the idea here is we observe 4 observations. X is 1, 2, 3, 4. There's random noise in these observations. So I get 4 observations, and based on my 4 observations, I make a prediction line. Maybe my prediction line is this purple line, okay? Maybe the 4 random observations I get happen to kind of have a fairly flat slope. So, so if I extend this and I say, okay, let's make a prediction, new prediction, where X is at 100, okay? And I come all the way out here, all right? This is going to be my prediction. Okay, you get a different sample. You observe when X is 1, 2, 3, 4. And because of your observations that you get, maybe you fit, say, this yellow line or the green line, okay? Because you got some random noise. And so because we're extrapolating all the way from here to here, your value could be as high as this, right? And so if we're trying to make a prediction where X new is 100, and we've only observed values of X around 1, 2, 3, and 4, we've got this huge amount of variation. Okay. And again, we just are taking or assuming our sigma squared is 1 here. But you know, if the observations themselves have even greater variance, you know, then it's going to get multiplied by even bigger factor. But let's just assume sigma squared is 1 for all of these things. And so trying to extrapolate way out here is going to produce, you know, pretty bad results. Okay. Okay. Just the same kind of thing happens if you extrapolate in the opposite direction. Okay. So you might be like, so we have X is 97, 98, 99, 100. And our new observation is at 1, 0. Then we also have a huge amount of variation. Oops. There as well. Okay, I don't have a picture going with that one. But same kind of idea here. So it's not, it is kind of interesting that it really just kind of reflects what, because you think about like, what does X transpose X inverse do? And you think, well, maybe it's because, you know, our values are huge or small or something, but it's something more interesting than that. There's kind of a relationship between, you know, the values you get in here and then the X new value. So if X transpose X, if you take your X values, the observed X values are at 1, 2, 3, 4, and you do X transpose X inverse, and your new observations at 100, you get a huge amount of variance, kind of like this. And you can kind of flip it around the other way, where your observed X values are near 100, 97, 98, 99, 100. And then now we try to make a prediction around X equal to 0. And then, and this variation is also huge, around 1,940. Okay. Here, let's say we have, these are my observations, 0, 50, 100, and 101. Okay. 0, 50, 100, and 101. And I say, all right, let's make a prediction if we have a new observation at 50. If we have a new observation at 50, let's make a prediction here. And what do we get? We get 0.273. 0.273. So pretty small variance. All right, and that again, kind of that makes sense. You have You have a point at 0, a point at 50, a point at 100. Okay. What if I get rid of this point at x equal to 50? Okay. Is that going to have an effect on the variance that I see? A little bit, but not that much. Okay. So it went from 0, 50, 100, 101. And basically, what if I cover up this middle observation at x equal to 50 here? Okay. If I cover up that middle observation, and so I just have a value at 0, I have a value at 100 and 101, and I'm trying to make a prediction at 50, I have just a touch more variance, but not that much more. I went from 0.273 to 0.376. Okay. And kind of the prediction picture looks kind of like this. I've got an observation at 0, 100, 101, observation at 50. Okay. So again, the random dots that I get, those are these little red dots. And again, I might get some observations and I might fit this blue line. You might get some random observations and you fit either the pink line or the orange line or something like that. How much are my predictions going to vary from your predictions? Probably not that much. So we have very little variance here. Okay. What if we get rid of this observation at 50 and we fit a linear model here? Okay. We fit a linear model, 0, 100, 101. We get rid of that observation at 50. How much is my prediction going to vary from your prediction? Again, probably not dramatically. And so again, we still have very, very little variance from here to here. Okay, if you and I are both fitting linear models here. But watch what happens if I decide to fit a quadratic model. Okay, watch what happens if I decide to fit a quadratic model. So here, my quadratic model, I'm going to have a column of ones. So my X matrix, I hope you guys can see this. Okay. My X matrix, I have a column of ones for my intercept. I have a slope, 0, and my X values are 0, 50, 100, 101. And then I have a kind of another coefficient for an X squared term. And so those values are 0, 50 squared, 100 squared, and 101 squared. And I want to say, okay, let's get a new observation where X is around 50. Okay, where X is 50. So here I'm going to have a new value, 1, 50, and 50 squared. And then I plug that in and I get X new, X transpose X inverse times X new. And the variance of my predictions is right around 1. Okay, right around 1 if I plug this in. All right, what happens if I get rid of this observation right here at 1 is 50 squared, right? So if I cut that observation out, okay, so if I remove this data point at 50, and then I say, all right, I have a point at 0, a point at 100, and a point at 101, and I want to make a prediction where my new observation is 50. Look at what happens. If I do X new, X transpose X inverse X new, now my variance is 1,262. Okay, so we get something wildly different, right? So we go from 1 to around 1,200, 1,300, whereas cutting out that observation at 50 back here hardly did anything. It went from 0.273 to 0.376. Okay, so removing an observation, so we have less information. So sure, our variance went up a little bit, but only a tiny bit. With the quadratic one, if I remove one observation, suddenly I have way, 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 way more variance. And so the question is, why? What's going on here? Okay. And what's going on is if you have observations that say 0, 50, 100, 101, and you're going to fit a quadratic model. And again, I don't actually know what those values are. It doesn't really matter. We just know that there's kind of constant variance throughout. But let's say we have values right here at 0, values right here at 50, values right here at 100, 101, and I'm trying to fit a quadratic line to it. This might be the lines that I fit. okay? And so all of the lines are all going to be kind of similar to each other, because right now our assumption is we have kind of constant variance around like the true values. So if I observe a value at 0, I might get 3. You might, by random chance, if you observe a value at x equal to 0, you might get 4. By random chance, if you get a random value at x equal to 0, you might get 2 or something, right? And then, for 50, again, the values you observe and the values I observe will be a little bit different from each other, but they're all going to be kind of in the same range. And the values at 100 or 101, the values you observe and I observe will be a little bit different from each other, but again, all within the same range. And so when we fit our lines that fit these, they all have to look kind of similar, okay? If I get rid of this point at 50, okay, I observe some random values at 0, x equal to 0, and values where x is 100 or 101, and you observe some values at x equal to 0, 100, 101, and we're going to fit a quadratic model to it, okay? Because it's a quadratic thing, there's a lot of kind of flexibility. And so depending on what these values end up being over here and what this value is over here, I could end up fitting the purple line, okay? You might end up fitting the green line or the yellow line or the red line or the blue line, okay? We might fit any of these things, and we don't really have an observation at x new 50 to kind of anchor this down. And so we're going to end up having lots and lots and lots of variance here. Okay. So I don't know, that to me, I think this is kind of interesting that this is all kind of reflected, um, you know, in a relatively, it looks fairly innocent, this x new, x transpose x inverse x new. You're just like, okay, let's take our new observation, let's take the observations we've seen so far, and yet this calculation here kind of reflects a lot of kind of like the underlying information here. Okay. What would happen? What do you think would happen if I do 0, 50, 100, and then and we're going to make x new at 101? So let's see. So if I do, we're going to plug in 50 and 50 squared, and we're going to make a prediction at 100 and 100 squared. Okay. So if I do that, so 0, 50, 101, these are my observed values of x. This is quadratic. And then my new observation is going to be at, can you guys see my RStudio, or do I have the wrong window shared? Okay, you can see it. All right. So we're going to put in our x new at 100, 100 squared. What do you think? We're going to get a variance on the order of 1200, variance on the order of 1, or something in between. Let's see. We get variance on the order of actually less than 1, 0.94, okay? Because here the value I'm observing at 100, okay, is in between. I've got 0, 50, 101. These 3 points kind of anchor wherever this kind of quadratic line is going to end up being, okay? Now, if I expand out to say 1000, okay, now we're going to have a huge amount of variance, okay, because as we extrapolate to somewhere far away, it gets wildly different. But if I were to say, if I said I observed something at near 1000, okay, we get a lot less variance, okay? if I say, if I've observed something at 0, 50, 100, and I want to try to predict something around 500, okay? We get a moderate amount of variance, but not a ridiculously huge amount, okay? If I bring something in near something where I've observed around 50, then we get basically basically 1 right there, okay? Also similar to if I put in something around 0, we're going to get basically if you plug in something near where you've observed a value, you're going to get a little bit of variance there, okay? And it's just kind of like when you do something where you haven't really seen anything, at least on this quadratic one, you get a little bit more variance there, okay? But again, if I bring in like a third term, like if we try to fit like a cubic model, actually, I think we're going to get infinite variance because you need at least 4 points to define a cubic model. And so if I only have 3 observations and I try to do a cubic model here, I think it's going to explode on me. Try. These are just ones I'm just fiddling around here. Ooh, this is gonna. Let's go back to 100 and 100 cubed. This might break my computer. Yeah, I get a singular. Let me just plug in one more here. Did you have a question? Oh, 100 and 100 cubed. Okay, so that works okay. But I think if I try to bring in something like 75, an observation around something somewhere where we haven't seen, we get quite a bit of variance, bringing in points near where I've seen, around say 50. Yeah, the variance of only around 1. I think 25 is going to reflect something similar to 75. The amount of variance we'll see, yeah, quite a bit. As I get closer to say observations that I've seen, okay, so if I'm going to plug, so I've seen observations 0, 50, 100, 101. Let's try out 2. We get something moderate in between there, okay? 49 will be, a little bit of variance and stuff. So I don't know. I think it's kind of interesting that that this all takes into account, because if you say like, all right, what does X transpose X inverse looks like? This is like hard to make sense of, right? Let's round this out just so places. Okay. So, these numbers, 1, negative 0.400 or something like that, right? These numbers somehow take into account basically the observations we've seen, and then when we multiply it by kind of these, our new observation, it all gets factored in there, which again, in my opinion, these things look kind of unassuming. And yet it reflects, yeah. It reflects kind of the internal variance here. So again, if I say, what is X transpose X inverse? Somehow this thing, 1, negative 0.20 and negative 0.02, 2, negative 0.02 and something, this is able to kind of take into account that like, oh yeah, if you plug in values around 50, it ends up huge, whereas values around 100 end up being small. And so I think that's kind of I think it's right, you know. Okay, so anyway, that is variance in the predictions. My hope is that these pictures give you a little bit of insight as far as like how taking into account the X values that you've seen and where your X new observation is will provide some information regarding how much variation there is going to be in the prediction that you make. Okay. I haven't given you any of you quiz answers, have I? Okay, let me give you your, I guess I'll go ahead and give you your first two. C and B, cat and bear. C and B. Okay, first two answers for today. All right, and then part two of our lecture is we will look at the multivariate normal distribution. Multivariate normal distribution is basically our normal distribution, but in a multivariate setting. Let me pull up. Let's go to the Wikipedia. And it looks like this, okay? Our, so this is kind of what a multivariate normal distribution might look like. If a two-dimensional multivariate normal distribution is often represented with something that looks like an ellipse, looks like a cloud of points or something like that, okay? So that's what we've got going on here. So kind of this cloud of points that looks like an ellipse. What you see here is that if you were only to look at the y observations, okay, so just completely ignore x. So if you either integrate out x or I guess the idea is if you just kind of let the all of these dots fall down, you end up getting a normal distribution in the y direction. If you also look at just the in the x direction, right? So basically just ignoring one of the columns, you also get a normal distribution there. So the multivariate normal is if you kind of integrate out or just collapse one of the variables. So I guess another way you can think of this is you got a matrix of points, right? Your two-dimensional data. So maybe you have 10,000 observations, 10,000 little dots here. But each observation is a pair of points. You got an X, you got a Y. And if you plot all of those XY coordinates, you get this kind of ellipse looking thing where you have a concentration in the center. And there's correlation between X and Y, but you got this kind of ellipse looking thing. But if you just take one column, like you have a column for X and a column for Y, if you just take that one column X and you say make a histogram of X, you get this thing. If you say, hey, let's take that column of Y, make a histogram of Y, you get this histogram over here. And those are both normal distributions. So X is normally distributed, Y is normally distributed, and that's what it looks like. Let's see what Wikipedia has to say. Multivariate normal distribution, also known as the multivariate Gaussian distribution or the joint normal distribution. It's pronounced Gaussian, by the way, not Gaussian. Gaussian because it's named after Gauss. Is a generalization of the univariate normal distribution to higher dimensions. Okay. One definition is that a random vector is said to be k-variate, or like, two-dimensional, three-dimensional, four-dimensional, whatever, normally distributed if every linear combination of its k components has a univariate normal distribution. So if you take just x by itself, you get a normal distribution. If you take y by itself, you get a normal distribution. And then if you take any linear combination, so I think in 100B, you guys learned this, right? If x is normally distributed and y is normally distributed, and you do like x plus y or whatever, that also ends up being normal. Okay, well anyway, that's what you have. All right, multivariate central limit theorem. Okay, So this is the PDF. This is the PDF, and let me switch back to my slides here. So first, this is the PDF of the univariate normal distribution. You have x values. They come from a normal distribution. The PDF of that is 1 over root 2 pi sigma squared e to the x minus mu divided by 2 sigma squared. Okay. Now we have a vector of x. Okay, could be d-dimensional. Let's just use x as 2-dimensional. That'll make it easier for us. But anyway, basically you have a d-dimensional vector for the center. So if it's 2-dimensional, it might be something like 0, 0, or it might be centered at 100, 50, wherever, right? And then you have a square matrix sigma, a d by d square matrix. So a 2 by 2 if it's 2-dimensional, okay? And what is the corresponding density? The density function looks like this. You have 1 over square root 2 pi, and then raised to the d, however many dimensions you have. And then instead of sigma squared, you have the determinant of the square matrix sigma. Okay, so the determinant is equal to, I guess, the area of the, if you have this, if you think about what sigma is, you get this 2 by 2 vector, or 2 by 2 matrix, and you can kind of take those columns and make vectors out of them, and then you'll get like this little, you'll get like a parallelogram, right? So if you take one vector and it's pointing in this direction, and another vector and it's pointing over here, and you kind of fit out the corresponding parallelogram, so you get something that looks like this. What is that area? That's the determinant, okay? And you know, interestingly enough, it's kind of the well, this is a square matrix. So if you take the determinant of that, you know, there's similarities to that, and just kind of taking the values, doing sigma squared there. Okay. And then if you think about what's happening as far as the e part, you know, exp of whatever, okay, e raised to this, look, you have -1/2, that's right here, -1 over 2. And then you have x minus mu squared, and we have the vector x minus the mu vector transpose x vector minus mu vector, right? So when you're dealing in vectors, you don't square things, you do this transpose this, right? So x transpose x is kind of your idea of x squared there. So I have x minus mu transpose x minus mu. And then there's no division in linear algebra. You can't divide by a matrix, but you can multiply by the inverse. And so we're taking our kind of our square matrix sigma, and we invert it, and we do sigma inverse, right? And so we have that, okay? And so this, if you look at this, x minus mu squared divided by 2 sigma squared is basically 1/2 x minus mu transpose x minus mu, but we're going to put in sigma inverse here. So so parallels between the univariate and the multivariate PDF, okay? So here's something that looks, so here we have a 3-dimensional univariate multivariate thing. If your sigma matrix is the identity matrix, okay, then we have no covariance between our x variables. x1, x2, and x3 are all independent of each other, right? Covariance between x1 and x2 is 0. Covariance between x1 and x3 is 0, and a covariance between x2 and x3 is 0. Okay, then this will boil down to 3 univariate matrices that can be multiplied together, okay? So, oh, and then here, if I have my mu vector is just all zeros, okay? Then my multivariate PDF can be factored into 3 independent normal PDFs. So if I have this, I've got 1 over root 2 pi to the 3rd power. And then here, the determinant of the identity matrix is just 1. And then the inverse okay? The inverse of the identity matrix is also the identity matrix. So my PDF becomes 1 over root 2 pi to the third power, okay? And then, and here I have e to the negative 1/2 x transpose I x x, okay? And so if I take x and I that can just be factored into x1 squared plus x2 squared and x3 squared. And that can then be factored into the product of 3 standard normal distributions, okay? So that's simple enough. If you have any kind of d-dimensional thing and it's just diagonals and everything else is zeros, all the non-diagonal entries are 0, okay? Then you can show that we can factor this into a product of univariate normal PDFs, okay? So we have a so they don't all have to have variance 1 and mean 0, okay? You could have a bunch of different means and a bunch of different variances down the diagonal. But if all of the off-diagonal elements are 0, then but you can factor it out, okay? Again, thinking about what is the inverse. The inverse is just going to be a diagonal matrix, but just 1 over sigma squared down the diagonals there. And then your determinant is going to be basically all of these sigma squareds, there's just a big product of that. And so you can kind of factor that product into each individual sigma squared component, sigma 1 squared, sigma 2 squared, sigma to the d squared, sigma d squared. And then with the inverse, you can factor out basically each diagonal element as well. So basically, the resulting PDF, if all of your off-diagonal elements are 0, is just the product of a whole bunch of normal distributions, as one might expect. And so this is all kind of just reflected in our the formula, the PDF there. Okay. All right. What if we have non-zero values in the off diagonals? So here I've got a 3-dimensional vector. All right. X exists in 3 dimensions. Here are my mu's. Okay. This is the mean of x1, mean of x2, and mean of x3, and this is my sigma matrix. And so what we see is that there is covariance between x1 and x2. The covariance is 2. There is no covariance between x1 and x3. x1 and x3 are independent or orthogonal of each other. And x2 and x3 do have covariance, but negative covariance there, okay? The marginal distributions, if you were to just kind of take your column of x values, x1 values, and collapse it, it would have a mean of 1 and variance of 4, or sigma squared of 4. Your marginal distribution for x2 is be negative 1 with a variance of 1, and for x3, you would have a mean of 2 and a variance of 9, okay? And then we have kind of covariances here. So that would be what this kind of thing looks like. All of the subsets will also be kind of multivariate normal. So if I were to subset x1 and x3, x1 and x3 would have mean vector 1 and 2. Basically, I do that. And then looking at 1 and 3, I would have 4, 0, 0, 9. So x1 and x3 would be are independent of each other. Their variances, they're orthogonal, and so you would just kind of get that. You can basically take any other kind of subset of the variance matrix as well to get all of these things. If x comes from a multivariate normal distribution, okay, and you have some kind of non-singular matrix C, okay, square matrix C here, and you take the product, okay, of X and C. Basically, you're defining a new variable, Y, which is just a linear combination of your X variables. So it's kind of going back to our definition up here, okay? So one definition is that a random vector will, if every linear combination has a univariate normal distribution, I guess here we're kind of just saying like, if it isn't a multivariate normal, then any kind of linear combination, basically our Y hat is just, you have some matrix C, which is going to basically define a linear combination of the variables of X, okay? Then this will be normally distributed. So for example, X could have this normal distribution, 1, 2, 1, 0, 0, 3. So X is really, I guess, you have independent things. And we're going to define Y. We're going to have the first component of Y be x1 plus x2, and then the second component of Y be x1 minus x2. And that can be represented by this matrix C. We'll have 1, 1, and 1, negative 1. Okay? And so you can see when you do C times X, where X is x1 and x2, you can see, yeah, when you do this, you'll get 1 plus, or x1 plus x2 on the top, and x1 minus x2 on the bottom, and that's going to be my definition of Y. Okay? And so what is the mean going to be? The mean is going to be, I'm going to take C and multiply it by my mean vector 1 and 2. So on the top, I will do 1 plus 2, and I'll get a mean of 2. And on the bottom, I'll do 1 minus 2, and I'll get a mean of negative 1. So Y will have a mean of 3, negative 1. And if you do this, what's your total variance going to be? Well, I'll do C sigma C transpose. And so now we will have more variance, 4. And then there's covariance now between the top and the bottom of Y. We have covariance of negative 2. Okay, which is interesting. You got, if you have two independent X values, X1 is independent of X2, but if you're going to make a new thing of X1 plus X2 and X1 minus X2, those things will end up displaying covariance. Okay, and then what is the resulting, oh, I guess this is just a little bit of proof or derivation showing that relationship. Sure, what's the expected value of Y? Then the expected value of Y can be shown to be, okay, well, Y is defined as C times X. It'll be the expected value of C times X, which is just going to be C times the expected value of X. Expected value of X is mu, so it's going to be C times mu, so no surprise there. What is the variance of Y? Okay, the variance of Y is basically Y minus the expected value times Y minus the expected value transpose. And if you kind of go through it, you will see that you can factor out the C's, and you'll get C expected value of X minus mu, expected value of X minus times X minus mu transpose. Expected value of that, that's just the definition of sigma. And so you get C sigma C transpose. Okay, that is it. I will go ahead and give you your final view quiz answer, which is, I gotta look this up. Week 6, Mondays. The letter E. E is your last view quiz answer. All right, we will end here. Thanks for coming. We'll see you guys on Wednesday. All right, have a great rest of your day.